Oh, I didn't see you there. You startled us.
You caught us doing some light reading on the role of microbiology in developing treatment for cancers.
Yeah. I was just on my phone. I don't understand all these crazy, weird words.
Well, Chris, it's not that hard. Let me break it down for you. We'll start with an overview on cancer.
In order to understand how microbiology is playing a role in the understanding and treatment of cancer, we need to understand how cancerous cells develop. First, let's look at the growth cycle of a healthy cell. Proto-oncogenes are genes that are present in normal cells, but become cancerous when they are altered. When unaltered, the proto-oncogenes encode proteins that function to stimulate cell division, differentiation, and program cell death. When this gene is overexpressed, it becomes an oncogene. This leads to an overproduction of proteins, causing an abnormal rate of cell reproduction. Point mutation, deletions, or insertions can all cause overexpression of the gene and increased transcription, which renders them cancerous. The pathway by which healthy cells become cancerous is a multi-stage process known as carcinogenesis. The first step, called initiation, is the irreversible physical alteration of genetic material. Chemical agents that cause physical alterations in DNA are known as carcinogens. Carcinogens can be radioactive or non-radioactive. Sunlight and radiation, two well-known carcinogens, form dimers on the DNA that can affect the expression of these genes. Tobacco inhalation, alcohol consumption, and asbestos inhalation are three examples of non-radioactive carcinogens. Once the first step is complete, the next stage is called promotion. Since the DNA has already been altered, it can take quite some time before it has proliferated into anything like what we imagine cancer cells to be today. Promotion is the longest step in the process and does not itself produce malignant tumors. The more frequent result of promotion is localized tumor production, like in situ benign tumors. If a cancerous growth is able to reach the point of the next stage, progression, it can spread and become malignant through metastasis. The final step is also irreversible.
Chris, did you get any of that?
Well, yeah, but I still have some questions, like the role microbiology has played in the treatment of cancer.
Well, you see.
Chemotherapy is one of the most common treatments of cancer. Chemotherapy treats cancerous cells by interrupting the cell cycle and slowing down or stopping their reproduction. There are two main approaches of chemotherapy: targeting cells in the process of dividing and targeting cells at rest. Taxol is one example of chemotherapy treatment that specifies cancer cells in certain phases of the cell cycle. This is called a cell cycle-specific treatment. Taxol fights cancer by inhibiting the microtubule structure within the cell. This ultimately results in the death of the cell because microtubules are part of the cell's apparatus for dividing and replicating. Another common treatment of cancer is the use of radiation. Radiation directly damages cellular DNA. This is able to weaken or kill cancer cells, but unfortunately, it can also affect healthy cells within the body, resulting in many harmful side effects. The oldest and most common method of treatment is surgery. Surgery can decrease the possibility of cancer formation because the initial stage of carcinogenesis, initiation, can be removed. However, surgery is usually partnered with the chemotherapy or radiation treatment we described before.
And that's that.
Well, that's great, but what's on the horizon for microbiology?
I'm glad you asked.
One of the fastest growing fields of study in cancer treatments is drug delivery systems, or the method by which we can get the right medicinal therapy to specific cells. While nanoparticles already are present in chemotherapies, they possess many properties that may make them useful in the pursuit of increased specificity and efficiency of cancer treatments. The beauty of nanoparticles is their surface area to volume ratio, as they are small enough to maximize the change for the receptors to come into contact with the substrates. Polymeric nanoparticles, polymeric micelles, and dendrimers are three examples of promising nanoparticles. While these examples are already known and fairly well studied, there is a new and interesting idea that would drastically increase efficiency and specificity. Basically, this is a bunch of nanoparticles bound to their drug of choice. The cool thing about this method is the sensitivity to light. When these photovoltaic nanoparticles come into contact with light energy, they are able to release their previously inactivated drug therapy locally, which would allow us to target the cancerous cells within a much smaller area.
Why are you still here?
We don't have anything more for you.
Go home, man.
Go home.
Get out of here.